Okay, kiddos. Here goes solutions to our practice quiz. Momentum, energy, work, power. What is the potential energy of the apple as it lands on the ground? So we have an apple, it's up in a tree, it's going to fall. So as it lands on the ground, means the height would be 0, and our answer then would be 0 joules. So this is actually the solution for number 2. See how I got confused too? But we know potential energy is mgh. So if our height is 0, it means our potential energy is 0, and like that. 2, what's the potential energy of the apple just before it falls from the tree? That would be when it's up here and it has a height of 15. So we'd say mass times g times height, and that gives us this many joules. Again, kinetic energy, potential energy, work. So potential energy, kinetic energy, and work are all measured in joules. All right. Number 3, what is the kinetic energy of the apple as it lands on the ground? So what I've drawn here is a graph of, we have time, so as time goes on, what's going on with the energy? Kinetic energy is going to increase as time goes on. Potential energy is going to decrease as time goes on because the apple is falling. So at the top, you see potential is 588, kinetic is 0. By the time it reaches the bottom, those have exactly switched over. Potential would be 0, kinetic would be 588. Halfway, they would be sharing, and each would be half of 588. So they do that. So this is kind of called the work energy equivalence theorem. What is the kinetic energy of the apple as it lands on the ground? You just have to kind of know that, hey, all this potential energy will have turned into kinetic energy by the time it lands on the ground. There was no calculating involved here. For question 4, how much work does gravity do in bringing the apple to the ground? So there are 2 ways to do this. One is knowing that work is equal to force times distance. And the force that gravity exerts on the apple, we call its weight, and that is mass times acceleration, so mass times the acceleration due to gravity. So the weight of the apple, and then times the distance that it goes, that gives us 588 joules. Notice how that is the exact same number that we got for the kinetic energy down here, or the potential energy up top. So gravity is the thing that actually speeds the apple up. All the work done went into increasing the kinetic energy to this. So same as mgh, or potential energy, same as the kinetic energy gained by the force of gravity moving it through some distance. Number 5, how fast is the apple going as it hits the ground? So that's where we use the fact that it has this much kinetic energy, and kinetic energy is related to velocity by 1/2 mv squared. So we plug in kinetic energy and solve and get this. Now, as it hits the ground, this doesn't mean as it hits and then stops. It would obviously be 0, but it's referring to right before it actually hits. So like right there. Okay. If it said after it hits the ground, then it would be 0. Okay. Page 2. How fast is the apple going at a height of 5 meters? So this is a different situation. At a height of 5 meters, if it started at 15, it has fallen 10 meters and is 5 meters above the ground. So watch out what you have and where you're plugging them in. Okay, we could say that potential energy is equal to this, which gives us this number of joules. So that's the potential energy here. The potential plus kinetic will always be 588. So the 588 we can describe as total mechanical energy. So if the total mechanical energy is 588, it has lost a certain amount of potential energy that has gone into kinetic energy. So we were doing something like this, where we know that the potential plus the kinetic has to be 588. So you could write something like potential plus kinetic equals total mechanical energy. Total mechanical energy, which in this case is 588, to solve and determine that at this point its kinetic would be 392. Notice how it's more than the potential because it's more than halfway down. From that, actually solve for velocity saying 1/2 mv squared, and how fast was it going? Oh shoot, what was the answer? Pretty sure it was this, 17.1. So we have 1/2 mv squared equals 392. And plug in our 4 here and divide and take the square root. And I think this was the answer. But you better check me on that. Number 7, de Wolf pushes with a force of this on a crate with this mass on a frictionless surface. It takes him 3.1 seconds to push the crate 30 meters. So here's my diagram. We have a bunch of information: frictionless, mass, force, distance, time. Let's see what we can do. 7, how much work does he do on the crate? Work is just force times distance. So he's exerting a constant force through some distance. We multiply the two together, 6,000 joules. Okay, so that 6,000 joules is work that de Wolf does on the crate, which is going all into kinetic energy. None's being lost due to friction, and it's not moving up or down. So somewhere down here, we're going to use the fact that 6,000 joules of work was done, and that all went into kinetic energy. Let's see. In question 8, what is the weight of the crate? So again, weight, W equals mg. Don't fall for this. Okay, that is the mass. This is obviously wrong. Mass is measured in kilograms. Weight is measured in newtons. So this is newtons versus kilograms. Okay, please know the difference. Kilograms for mass. Newton, that's a measure of force. That is for weight. So solving gives us this. Newtons, 313 newtons. What is the initial kinetic energy of the crate? So initial means right here. And though the question doesn't explicitly say it starts from rest, oh wait, it does. The crate starts from rest. So, okay, we know that it starts from rest. Initial velocity would be 0, so initial kinetic energy would be 0. Number 10, how fast is the crate going by the end of 30 meters? So you could use your old kinematics equations to solve, and it would give you this, but using energy, or the concept of energy, is usually easier. So the work done in this case all went into kinetic energy. And in this case, it all went into kinetic energy because there's none lost due to friction, and there's no potential energy gained or lost. So all the work done had to go into kinetic energy. So we know that 6,000 joules went into kinetic energy, so the new kinetic energy is not 0, but is now 6,000 at the end of the run. We set that equal to 1/2 mv squared. We solve for v and end up with that many meters per second. And then how much power does de Wolf exert? So power, work per time. He did 6,000 joules of work over the course of 3.1 seconds, divided and ended up with something like this. Notice the units, that is watts. Okay, so a watt is a joule per second. All right, that's it for now. We're going to look at the second part in video lesson number 2.